All right, it's time to talk periodic table trends. Are you ready? All right, here are our objectives, the standards. Pause it and peruse it if you want, but I'm just going to get right to the content. All right, so here's the arrangement of the periodic table, the modern periodic table. And if you recall, it is arranged by atomic number. And when you arrange it by atomic number, we are going to have repeating patterns based on the number of valence electrons. And the number of valence electrons, remember, determines properties, how elements react. And that is why we see those repetition of properties. So what is the periodic law? So when we arrange the elements according to their atomic numbers, elements with similar properties appear at regular intervals. And remember, that is because the valence electrons. So the elements in group 1 are all going to have one valence electron. So the properties repeat because of the valence electron, so the way that the periodic table is arranged. So again, the periodic law states that physical and chemical properties of elements periodically repeat based on their atomic numbers, but it ties to, remember, valence electrons. So periodic trends. Well, a trend, you should know, is a predictable change in a particular direction. So tends to increase, tends to decrease, tends to stay the same, a trend. And the arrangement of the periodic table reveals trends in the properties of these elements. And we're going to talk about a few of these trends. So the first one is ionization energy. So you don't need to memorize these values. So if you look at table S, one of the columns says first ionization energy. Well, let's talk about what ionization energy is first, so then you can see what that means to use that qualifier first. Well, ionization energy is the energy required to remove an electron from an atom or ion. So here's the atom with its electrons and its energy needed to pull one of those electrons away. And because it says first ionization energy, it's the energy required to pull away the first electron. There would be other values for second ionization energy and so on, but we are only going to focus on this one, the energy needed to pull away that first electron. You don't have to guess on the numbers. You can look them up on table S. Understanding the trends helps. You don't have to look every single thing up. But again, this is not a memorized thing, but through practice, you should be able to retain it. So first ionization energy. So here are the ionization energy details. Remember, you don't need to memorize it, but again, it helps to have a good, clear picture of it. So ionization energy across a period. Remember, periods are horizontal rows on the periodic table. So as we go across a period, we add a proton and electron. Remember, atoms are neutral. So if I'm adding a proton, I'm adding an electron. So as I'm moving across the period, I have a proton and electron added as I move across each element. This increases the nuclear charge. So the nucleus is going from a +3 to a +4 to a +5 to a +6. Okay, the nuclear charge is increasing. But those electrons are being added to the same energy level. So remember, the period tells me how many occupied energy levels I have. So I was just giving examples from period 2, +3, +4. Well, those are all in the second energy level. So I keep adding more to the nucleus and more electrons to the same energy level. As a result, those electrons are more strongly attracted by that nucleus. So the electrons have a negative charge, the protons have a positive charge. So the ionization energy increases. Why? Those electrons are held a little tighter, so it's harder to pull one away. So the ionization energy would increase. All right, what about down a group? Well, as we go down a group, the groups are vertical columns. The number of energy level increases as you go down a group. So this increases electron shielding. We're adding energy levels, okay, the relative size of the atom increasing, and we have all these other electrons in the way shielding that pull from that positive nucleus. So as we have that increased shielding, adding more and more energy levels, it reduces the attraction for the outermost valence electrons. So the electrons are less strongly attracted. So remember, we're only talking about pulling away one of the valence electrons. So the ionization energy decreases. So let's look at that as a visual. So as we go across a period, the ionization energy goes up. As we go down a group, the ionization energy goes down. So this table right here shows the ways that it increases. So if I look at this, that means the area around fluorine would be the highest ionization energy, and the area around francium would be the lowest ionization energy. All right, so as you go down a group, what happens to ionization energy? It decreases. As you go across a period, what happens to ionization energy? It increases. All right, so let's talk atomic radius, okay? Now, since atoms are so small, it's relatively hard to measure the radius of an individual atom. So we do it kind of in a different way. We take the radius of two bonded atoms. So we take the measurement from the nucleus of one atom to the nucleus of the next atom when they're bonded, and then we have that distance to get the atomic radius. So kind of a weird way we get it, but anyway, the values are still on table S. And it is a little bit hard to determine, so we use the bond radius. But again, you don't have to guess for these values. They are on table S, but it does help to have a kind of an idea in your head so that you have less to look up. Because if you have to look up everything, sometimes you run out of time. So again, look at table S for the values, and let's look at the trends. So here are the radius details for atomic radius. Remember, you don't need to memorize. So across a period, remember, period is a horizontal row. Again, if you remember from the last one, more protons and electrons are added as you go across a period. This increases the nuclear charge. Again, this should sound familiar. The electrons are being added to the same energy level. Seems like I said this before. So the outer electrons, in fact, are pulled a little closer. So remember, the ionization energy was harder to pull the electron away. Why? Because those electrons are being pulled a little closer. So in fact, the radius decreases slightly. So as we're going across a period, the radius actually decreases. Now let's look about down a group. So remember, groups are vertical columns. As you go down a group, this should sound familiar. The number of energy levels increase as you go down a group. The electron shielding increases. Remember, we have more energy levels with other electrons inside, so that kind of shields that pull from the nucleus. The nuclear charge stays relatively constant, so that the effective nuclear charge stays relatively constant. So those outermost valence electrons are not pulled any closer. So the atomic radius is going to increase. So as we go down a group, we're going to start small and get bigger as we go down a group. And mostly because we're adding additional energy levels. That's how I like to think about it. So atomic radius, the size of the atom. So you can see here's a relative representation. You can see as you go across a period, the atomic radius decreases, and as you go down a group, the atomic radius increases. So again, around where you see rubidium on this section of the periodic table, that's where you have the largest atoms, and then up where you see helium is the smallest. So as you go down a group, what happens to atomic radius? It increases. As you go across a period, what happens to atomic radius? It decreases. Okay. All right, so now let's talk electronegativity. So we have another value on the table S. Electronegativity is the measure of the ability of an atom when it's bonded to attract an electron. So it's like kind of thinking about it like the opposite of ionization energy. So again, you don't have to guess. The values are found in table S. It does help if you have an idea and if you do remember some of it, but again, You don't have to focus on memorizing values for sure, but trends, it's good to have an idea. So here are the electronegativity details. Remember, you don't have to memorize. Okay, time to look at electronegativity across a period. So again, this should sound familiar. We get more protons and more electrons added as we go across a period. So in period 2, we start with 3 protons and 3 electrons, then 4 protons and 4 electrons, then 5 protons and 5 electrons, and so on. This increases the nuclear charge. The charge on the nucleus is increasing from a +3 to a +4 to a +5, and so on. The electrons are being added to the same energy level, right? So we're staying at, in period 2, we're staying at the second energy level. We're not moving up an energy level. The electrons are going to be more strongly attracted, which means it's easier to pull another electron in. So the electronegativity increases. It's easier to pull an electron in. So even though we're thinking about ionization energy as pulling an electron away and electronegativity as pulling an electron in, both of them have their values increasing as we go across a period. Now, as we go down a group, so this again should sound familiar. The number of energy levels increases. The electron shielding increases. We have those inner energy levels kind of blocking that nuclear charge. So the affecting nuclear charge stays relatively constant, again, because of that shielding. So since the size is increasing, the ability to attract an electron decreases. So the electronegativity actually decreases. So electronegativity, looking at it visually, it increases going across a period, and it would increase going up a group. Usually we talk about it going down a group, so it's decreasing. So it's increasing going across a period and decreasing going down a group. So as you go down a group, electronegativity what? Decreases. As you go across a period, electronegativity what? Increases. Okay, fluorine being the most electronegative element, you see it 4.0. I always think about perfect score, 4.0. And then cesium, you can see in this section right here, it has the lowest. So we're going to have the highest up here with fluorine and the lowest in group 1. Okay, now let's look at melting and boiling point. So again, these values are on table S. Notice that we use Kelvin, and again, we use Kelvin so we don't have to worry about negatives. It's real simple conversion from Celsius to Kelvin. You just add 273. Melting, remember, is going from a solid to a liquid, so it's at that temperature. So if you heat up something to the melting point, the transition is going to begin from solid to liquid, and it will remain at that temperature until that change is complete. Boiling is going from a liquid to a gas, so if you continue to heat it, and you get to the boiling point temperature, it is going to begin to change from a liquid to a gas. Keep it at that temperature. It's going to stay there until all of it changes from a liquid to a gas. So again, you don't have to guess for these values. They can be found in table S. It's just not as neat as some of the other trends we just talked about. So you can see these are based on the 4th, the 5th, and the 6th periods. And you can see that what happens is the melting points and boiling points, so it would follow a similar trend, go up and then down, and then there's another little kind of burst up and down, okay? But in general, it is not just increase or just flat decrease, but again, this would just be a matter of checking on table S. So the trend is a big increase, big decrease, and then just a little bump, okay? But you can see both the 4th and the 5th, and then also the 6th period follow that same trend. All right, now what about metallic character? So metallic character versus non-metallic character. So metallic character is how metallic an element is. So remember, metals lose electrons, okay? So they give up their electrons. So that means it would be easy to pull an electron away. So that means we'd need a low ionization energy. And where we have a low ionization energy is in group 1 at the bottom near where francium is. So that would be the most metallic, okay? So as you go down a group, what's happening to the metallic character? It is increasing, more metallic, easier to pull an electron away. Okay, what about non-metallic character? Well, so if metallic character is ability for something to lose an electron, to pull it away, for non-metallic character, we're talking about the ability to attract an electron. And that would mean have a high electronegativity, right? The ability to attract an electron. So where do we have elements that have high electronegativity? So remember fluorine, that 4.0, the perfect electronegativity, that is at the very top of group 17. So as you go across a period, non-metallic character is increasing. So metallic character increases as you go down a group, and non-metallic character increases as you go across a period. So the most non-metallic would be fluorine, and the most metallic, francium. So they're both Fs, they're just on different ends. Now, electron affinity. This is not in table S, but this is talking about the energy change when a neutral atom gains an electron. It sounds like electronegativity, pulling an electron in, but electronegativity refers to when atoms are bonding, and electron affinity just refers to when a neutral atom is going to gain the electron. But the trend is exactly the same as electronegativity. So I always think electronegativity, electron affinity, they sound very similar. They both start with electro. So their trends are the same. So if you know the electronegativity trend, you know the electron affinity trend. And they both have to do with pulling an electron in. It's just electron affinity is for a neutral atom. So as you go down a group, electron affinity decreases, and as you go across a period, electron affinity increases, okay? So let's put it all together in one visual representation so you can see largest, here, so let me bring this. Let's look at atomic radius. So atomic radius is increasing right here. So here, largest atomic radius, smallest atomic radius. All right, let's look at metallic character. So it says metallic character increasing going this way. So the most metallic, most non-metallic. Okay, let's look electronegativity and electron affinity together. This is the ability to attract an electron in terms of bonding. And this is the ability to attract an electron to a neutral atom. So you can see most electronegativity is going to be this one. Remember, these are noble gases, so they tend not to react. So we're going to stop here at fluorine, most electronegativity, 4.0. Beautiful, perfect. And then down here would be the lowest for electronegativity and electron affinity. And then ionization energy is literally following the same trend, okay? So highest ionization energy takes the most energy to pull the electron away, and then lowest ionization energy, easiest to pull an electron away, okay? So metallic this way, non-metallic this way, electronegativity, ionization energy, and electron affinity, they all go this way. So if you try and think about like remembering it one way, ionization energy, electronegativity, electron affinity, they're all increasing as we move up here. And so they'll be lowest over here. Atomic radius is kind of the oddball, increasing the other way, and metallic and non-metallic. So if you remember which side of the periodic table is metals, which is non-metals, this should be relatively easy to remember. Okay, so hopefully that makes sense, putting it together as one big picture. And that's it. That's periodic table trends. Today, I hope that you learned something new.